In a precision motion system, the guide surface is more than a place for a slide to move. It becomes a geometric reference. Every straightness error, worn contact band, mounting distortion, or local surface defect can be repeated again and again as the carriage travels the same path. The quality of motion therefore begins before the actuator moves, it begins in the rail itself. That is why a long ceramic rail has to be read as an interface, not simply as a long ceramic bar. One surface may carry or guide contact, another may register against a machine base, and the holes or slots may only locate the part. The function is created by the relationship between those surfaces, the mating component, and the way the rail is supported. Repeated contact places the track surface under wear, especially when fine abrasive debris reaches the interface. A representative 3 Y-TZP Zirconia grade has a Vickers hardness of about 1300. Hardness does not eliminate wear, and actual wear still depends on the counterface, load, speed, lubrication, and contamination, but it gives the guide surface a strong resistance to indentation and abrasive damage. Guide rails also contain holes, grooves, shoulders, and thin sections where local stress can concentrate. Stabilized zirconia is unusual among structural ceramics because its tetragonal face can transform locally around a growing crack, creating a shielding effect that resists further crack extension. A representative 3 Y-TZP grade reaches roughly 10 megapascal square root meters in fracture toughness, but careful radius design and controlled fastening are still essential. A guideway must also preserve its shape while loads pass through the moving assembly. The elastic modulus of a representative 3 Y-TZP is about 205 gigapascals, with flexural strength around 1000 megapascals. Those material values support a stiff structural component, but the actual deflection of a rail is still governed by section geometry, unsupported span, fastening pattern, and load position. Material stiffness is only one part of motion accuracy. Once the material is chosen, the motion problem becomes geometric. A carriage can only follow the reference that the guideway presents. Straightness, parallelism between working faces, and the relationship between the rail and its machine base determine whether the moving stage travels cleanly or inherits a systematic deviation. For this reason, guide rails are usually treated as precision interfaces whose final geometry must be verified after grinding and before assembly. The surface pair matters as much as the ceramic alone. A polished rail can reduce asperity interaction, but friction cannot be assigned from one roughness value without knowing the counterface and operating condition. Ceramic, polymer, or other mating elements create different contact mechanics. Fine particles can also turn a sliding interface into an abrasive system, so surface finish, cleanliness, contact pressure, and counterface compatibility must be considered together. Ceramic strength does not make mounting details optional. Point loading under a screw head, an uneven support surface, or forced alignment between mispositioned holes and introduce tensile stress into a brittle component. Long rails benefit from broad, clean support and fastening that locates the part without trying to bend it into shape. Chamfers, RD, local thickness, and hole spacing are there for structural decisions as well as machining details. Unlike a complete standardized metal linear guide series, a zirconia ceramic rail is commonly made around the machine interface it must fit. Length, width, thickness, track profile, and the location of mounting features can change substantially from one assembly to another. The important dimensional question is not whether a rail matches a universal size, but whether its working datums and mounting geometry match the motion system. For a build-to-print rail, the drawing should control more than overall size. Hole and slot positions, mounting pitch, datum surfaces, groove geometry, edge RD, flatness, straightness, and the relationship between mating faces all affect assembly. A longer rail also increases sensitivity to base alignment and support conditions, so dimensional review has to consider both the ceramic part and the structure beneath it. In a precision grinding stage, the guideway repeatedly carries the moving table along the same path while abrasive particles may be present nearby. A hard zirconia track surface helps resist progressive contact and abrasive wear, protecting the geometric reference that the stage depends on. The same stage also transfers workpiece and process loads into the guiding structure. Zirconia's high elastic modulus and mechanical strength support a rigid reference, while the rail cross-section and mounting base determine how much the complete assembly bends under load. Most importantly, the rail preserves the path the machine is trying to repeat. Hardness protects the surface, toughness protects local features, and stiffness supports the structure, but straightness and mounting turn those material advantages into useful motion. Precisely because the rail is a reference surface, every micrometer preserved at the guideway protects the motion built on top of it.